This talk is a quick introduction to combinatorial test methods for software and systems. I'll explain how this method works and also why it is so effective. It's important to point out that NIST is the U.S. government's measurement and testing laboratory, meaning we do research and better methods for testing and measurement, and everything we do is public domain, so the tools, the talk, and technical papers and other tutorials that are available at the website listed at the end of this talk, they are all public domain and available for free. We work with a lot of different organizations. These are just some that we've worked with in the past. This work is primarily on an informal basis, and we welcome further work with other organizations, so please contact us if you're interested. Combinatorial test methods can be used in a variety of application areas, primarily, of course, in software testing. And it's also important to note that these methods are good for detecting security vulnerabilities. One point is that we've discovered that about 2/3 of the vulnerabilities in security come from implementation faults, just ordinary coding errors such as mistakes failing to check input, buffer overflows, and that sort of thing. They can also be used for modeling and simulation. One of the problems with modeling and simulating systems is being sure that you cover all of the complex cases, but this method is sort of built-in capability for covering all of the rare cases, and you'll see why when we discuss it in just a few minutes. Performance tuning is another good application. One of the things that we look for in performance is making sure that we have the most effective combination of configuration settings, and by ensuring that we cover the important combinations, this method can be very effective for performance tuning as well. So basically it covers application areas and test areas where you have systems with a large number of factors that interact. This work began about 1999 when we were studying software failures, looking at 15 years of recall data from the U.S. Food and Drug Administration on medical devices. So we were looking at all different causes of software failures, whether they were logic errors, numeric errors in calculation, input checking, and so on. One of the things that we looked at were interaction faults. And by that, we mean an example such as this, where we have a failure that occurs only when the altitude is at some level and the volume is less than some number, for example. So that's two factors interacting. This is called a two-way interaction. So if we tested all pairs of values, we could find this fault. But that's really not enough to look at pairs of values. We could have single factor faults. That's fairly obvious, where we have a system or an application that fails when one condition is true. We've already just given examples of two-way interactions, and in general we could have higher level interactions where we could have 3 or 4 factors involved in failures. And so that's one of the things that we looked at. We have an example here of a single factor fault. That's the first one. The second is a two-way interaction. The third involves 3 factors, 3 conditions that have to be true before the failure occurs. So what this means is that a failure would only occur, in this case, in the third case there, if all 3 factors were true. And even though pairwise testing was fairly common at this time, we discovered that no one had really looked at interactions beyond two-way interactions previous to this. So let's consider how these are distributed. So one of the things that's interesting is about 2/3 of the faults for this particular collection of data were caused by a single factor. And going up to either 1 or 2 factors, we got to about 96% of the faults were caused by either 1 factor or 2 factors. And going up to 100%, we never found more than 4 factors involved in a failure. But that is just one kind of application. So we started looking at others. this was open source server software. The interesting thing here is that these faults are harder to find than the medical device software. In other words, this profile is in some sense better than the medical device software because only 40% of the faults were caused by a single factor fault, and about 70% of the failures by either 1 or 2, and so on. And in this case, up to 6 factors were involved in failures. Open source browser software has a very similar profile. This was interesting because this is a distributed database software, but in this case, the test results were from the first time that the system had been tested. The other applications that we talked about, the browser, the server, and the medical device software, were fielded products, so products that were in use by tens of thousands, or in the browser and server case, millions, tens of millions of people, hundreds of millions of people. But in this case, this was just the first time the software was tested. So the blue curve here represents that first time testing for this database software. And the fault profile here is actually still better than the medical devices. The MySQL database, again, we see a similar profile. TCP/IP, again, very similar. And just collecting data from a large number of systems, we see very similar profiles here. So a couple of things that are worth pointing out. There are a few systems where only around 10% of the failures were caused by a single factor. And as we go up to 2-way, 3-way, 4-way, 5-way, and 6-way failures, the number of, or the percentage of failures decreases very rapidly. So we never found, and no one else has seen, failures involving more than 6 variables for a single system. And so this is kind of an interesting result. How does this help? Well, we can put this together, the empirical data together, into what we refer to as the interaction rule. So what this says is that all faults that we've seen, at least, are triggered by a small number of variables interacting. So what this means is that by testing all T-way combinations, all 2, 3, 4, 5, 6-way combinations, we can do testing that is in some sense pseudo-exhaustive and therefore can provide very strong assurance. As we all know, it's impossible to exhaustively test all possible input combinations for anything but the tiniest toy programs. But this interaction rule says that within reason, we don't need to do that. There are still timing issues, there are many issues that also have to be covered, but as a practical matter, the interaction rule says that we get very strong testing using a relatively small test set. So again, it's no silver bullet, but it has been validated on many real systems, and we have examples of many case studies in all different application domains on our website. So how would this work in practice? Here's an example that I think most people have seen. We have 10 different options here that can be on or off. We can treat these as booleans, 0, 1, on or off. So we want to look at testing this complex set of combinations. Since there are 10 effects, obviously there are 2 to the 10th or 1,024 possibilities, but we probably don't want to do 1,024 tests. So what we could do is look at all 3-way interactions. So let's consider how many tests that would take. We have, again, 10 choose 3, or 120 3-way interactions. And each of these has 2 to the 3rd, because 0, 0, 0, 0, 0, 1, and so on, 8 possible settings. So that's 120 times 8, or 960 combinations. But each test includes many triples. Actually, it includes 10 choose 3, or 120 triples. So we want to know what's the smallest number of tests that would be required to test all three-way combinations. To do that, we can use a covering array. A covering array, in this case, of 13 tests covers all of those 960 combinations. So what this means in this array is that each row represents a test, and each column represents a factor, or a variable or parameter. So if we look at this first set here in red, we see that all three-way combinations of these parameters are covered. 0, 0, 0, 0, 0, 1, 0, 1, 0, and so on. And we can do the same with any other set of combinations, columns, inside out, left to right. Any way we want to choose them, we cover all 8 combinations. The math behind this was developed in the 1990s. It is a hard problem in theory, but for practical size problems, the algorithms that are available today work very well. Here's a much bigger example. In this case, we're going to consider a system that has a large number of on-off switches, and let's say that the software must respond in different ways depending on how these switches are set. So 34 switches, that means we have 2 to the 34th, or roughly 17 billion possible input combinations. We certainly don't want to do 17 billion tests, but if we think that no failure involves more than 3 switch settings interacting, then we only need 33 tests to cover all three-way interactions. We can cover four-way interactions with 85 tests, and so on. Only a few hundred are involved in testing all 5- and 6-way combinations if we wanted to do that. So what this means in terms of test effectiveness is that we can cover a very large percentage of the anticipated failures using a very small number of tests. So if we go out to a few hundred tests at most, we can cover all 5- or 6-way combinations. So that's much better than testing all 17 billion combinations. This is just a very brief introduction. There are many more tutorials and examples on our website, and we will be talking about those in other presentations. Thank you.